Okay, so these are the fundamental forces in order of strength. The strong nuclear force, but even though it's the strongest and it's the thing that binds the protons and neutrons together, it only operates over a really short range. It only has effectiveness at about 10 to the minus 15th meters. The electromagnetic force is the next. The strong force is way stronger than the electromagnetic force, but it has infinite range, and this deals with charged particles and protons and electrons, as well as photons, right? The photons of light. Remember, the photons are the exchange particle. All right, and then there's the weak force, which deals with radioactive decay. It is also a short-range force. Notice it's even shorter, about 10 to the minus 17th meters. Gravity, of course, is the weakest of all the forces, but it also has infinite range, and it really is the primary force when you're talking about astronomy, right? Astronomy is this is what guides the stars in their paths. Guides the galactic clusters and so forth, in forming superclusters, things like that. So gravity is the primary force that's involved, and of course we have two theories. Isaac Newton's theory of gravity works really well, as a matter of fact, and it still works very well. It's only when you get into extreme situations where you have to use Isaac Newton. You abandon Newtonian gravitation in favor, of course, of Einstein's theory of gravity. Einstein's theory of gravity is more accurate, is a good way of thinking of it. All right. So anyhow, let's look at this. This is showing, of course, that the weak nuclear force and the electromagnetic force are the same force at temperatures above 10 to the 15th Kelvin, of course. So in other words, the electro weak force freezes out. That is, but below the temperature of 10 to the 15th Kelvin, you get a separate force called the weak nuclear force and the electromagnetic force. All right. And this, by the way, has been experimentally proven. In the 1960s, we actually proved that above this temperature, you get this single force called the electroweak force. And then, of course, we have the grand unification theory that attempts to unite the strong nuclear force with the electroweak force, and so that's predicted to be at temperatures above 10 to the 28th Kelvin. However, this experimentally this eludes us, this temperature, and we've not been able to perform experiments to verify this yet. We hope to do that someday. And then theoretically, we think that gravitation would, remember, this would be conditions, that start to approach the moments right after the Big Bang. And so this would be about 10 to the 32nd Kelvin. We think that gravitation would unite with it would be like a super force that would be all four of them at above these temperatures. But again, you're talking about really approaching the moments after the Big Bang. All right, so those are the four forces. There are 6 types of quarks. The most common ones are the ones that make up protons and neutrons, the up and down quarks. These other quarks are, in fact, the last one to be discovered or experimentally verified was the top quark. In fact, one of the things that we think might account, although remember, put a big, huge underline might, account for the the dark matter. Remember, the dark matter does not interact with any form of electromagnetic radiation, but we think that if you take these heavier quarks and they go on to form heavier particles, like so again, neutrons and protons are roughly the same size, right? They're about the same mass. Neutrons are slightly more massive, but when you start to form particles with this other stuff, you would get things that are thousands and thousands of times more massive than a proton. And so if that stuff does not interact with any form of electromagnetic radiation, that could account for what the dark matter is, right? So that this is one of the things that people are exploring, that collectively are those things that would be made of these type of quarks, that first started in the early universe. I mean, these things were created in abundance, and at least our theories indicate that they were created in abundance during the quark epoch of the universe. Anyhow, if that were the case, these things would be, again, thousands upon thousands of times more massive than a proton or a neutron, and so maybe they could account for the stuff of dark matter, right? So that's the dark matter, right? Or maybe, we don't know, right? We don't know. And that's what we collectively call machos. That's what I was kind of trying to get at. All right, there are, of course, the leptons. The electron is the most is the one that we know about the best. There are also these things called muons and tauons, and then neutrinos, of course. There's a different type of neutrino associated with the electron. It's called the electron neutrino, the muon neutrino, and the tau neutrino. So anyhow, that pretty much sums up, although it's much more complicated than that, but anyhow, that sums up particle physics, basically. All right, so this is, as I just mentioned, these are, this is where the electroweak force comes into play above this temperature, 10 to the 15th Kelvin. We think that, all the experimental theoretical physics says that above a temperature of about 10 to the 28th Kelvin, you would unify the strong nuclear force with the electroweak force. And in some of these theories, so this is where, I think I mentioned this before. This is you get this thing called GUTS, the grand unification theory, and then there's SUSY GUTS, which is supersymmetric grand unification theory. Anyhow, this is just more of particle physics. So you get these supersymmetric partners, which again, this is another thing that that might be what the dark matter is, right? So if this supersymmetry theory turns out to be correct, we're still, again, I'm one of these people that, it's wonderful if we have all this math that describes these things, but of course we need experimental evidence for this to be, anything approaching what we would call scientific, right? We always have to have experimental evidence. All right, so, and this, okay, so this has become very popular, certainly in the last 20 years or so, and this is what's called string theory, okay? So string theory, the basic idea is to unite all the forces, right? And string theory, mathematically anyway, does this, and so it basically, it reduces even quarks and leptons into these little tiny strings, which are not observable. I want everybody to understand that this is not something it's just mathematical right now. These are on a scale well below. I mean, you got to understand, we can barely barely detect quarks right now, right? And you know, like the muon and the tau, and even neutrinos. I mean, it's really hard to do that. What string theory is proposing is that even on a deeper level, that you know, the quarks are these little vibrating strings, and they vibrate in different modes. But again, this is way smaller than quarks, right? So these things build up to become, you know, what we know of as quarks. I mean, quarks. It gets even more complicated because quarks can't even exist on their own, right? That they have what's called asymptotic freedom, which means that the more you try to pull quarks apart, the stronger the force gets. And so, you know, except in the very earliest stages of the universe, or in, you know, extremely advanced particle accelerators like CERN in you know, in Europe, and in Fermilab in Chicago, only at those extreme temperatures and extreme densities do you get, you know, you get any evidence of individual quarks. So this thing about strings is on a totally different order of magnitude. Like, these things would be way smaller than anything that we can even hope to experimentally verify. But with that said, all right, so even with that said, why has, during the last 20 and even 25 years of theoretical physics, devoted so much time to string theory? Because it works out very, very, very well that we can actually, what appears to be gravity, in a quantum field, like we can actually quantize gravity under string theory. But again, there's no experimental evidence for string theory. It's just one of these very elegant. It is extremely elegant. The mathematics is amazing, but again, it's not, you know, technically scientific, because we don't have any kind of experimental ways. And I don't know that any time in the near future we have any experimental evidence of strings. It would be nice. A few years ago, there was some experiment that it turned out to not be proving strings, but you know, people are always hopeful. All right, so this is the thing I looked at a little while ago. All right, so we have hydrogen being during the atomic era. You know, there's the formation of nuclei and atoms, in particular hydrogen and helium. But of course, there's also this thing called deuterium. This thing, H2. Right, so this is just a normal hydrogen atom with a neutron, or heavy hydrogen. Anyhow, this is kind of a the deuterium in the regular hydrogen form. This is actually a radioactive substance called tritium. And then, of course, if you have two deuteriums, you can produce this helium-3, and then the helium-3. This is just a process. Anyhow, this is where the helium comes from, and of course, our calculations show that about 1/4 of the available hydrogen turns into, you know, regular old helium, right? But see, remember, this is really hard to distinguish primordial helium, the helium that was created in the Big Bang, with helium that is, of course, in you know, that's going on in the regular fusion of in fusion of hydrogen into helium in stars nowadays, right? So but of course the deuterium, this is just a showing you this process. But the deuterium, which is shown right here as a proton and a neutron, that hasn't changed. That amount hasn't changed since the beginning of the universe. So that is a good indicator of the